Hey everybody, welcome to episode 12 of Forensics Talks. I normally do an introduction at the beginning, or should say some announcements and that sort of thing, but I'm actually going to skip that because we have a ton of material today to get through. My guest today is Dr. Leroy Hulsey, and he received his PhD in 1976 in structural engineering from the University of Missouri-Rolla. He's owned and run 3 high-tech engineering research corporations. He's taught at the University of Missouri-Rolla, North Carolina State University, and the University of Alaska Fairbanks. While at UAF in Fairbanks, he's been an active researcher. He served as department head and participated in numerous university committees. Dr. Hulsey focuses on working with students to achieve a high-quality education. His research is in the fields of bridge engineering and effects of temperature extremes on structural systems like composite wall panels for buildings. He's been an advisor for many graduate students, and of special importance for our talk today, Dr. Hulsey has experience in mathematical modeling using state-of-the-art methods in finite element, finite difference, and theoretical solid mechanics. So, Dr. Hulsey, I'm going to bring you in here, and first off, welcome. Thank you very much for your time.
Thank you so much for having me. Appreciate it.
We have a lot of stuff here, but first things first, I want to ask you about civil engineering and maybe think back. You've been doing this for decades now, and what was it about engineering that caught your interest when you first started?
I actually didn't really know anything about engineering. I was a carpenter working for my father, putting up housing, and I wanted to be an architect. But I was in the state of Missouri, and the only architectural school was a private institution, Washington University, and we couldn't afford it. So my father said, let's package you up and take you to this other school. And I just started discovering that there was a lot of similarities from what I was doing, except I didn't know why I was doing it. And so then through that process of really getting involved into understanding why we did certain things in construction, that was the lead in, and never looked back.
Right. Yeah, for sure. And you spent a lot of time. You spent a lot of time with a lot of PhD students and doing research. So research makes up a big part of what you do.
Yeah.
What I was reading in the beginning, in the introduction, was there a point where you started looking at some of the finite element methods, or is this something you've been doing a long time or more recently?
No, this has been a really long time. I actually developed finite element programs when I was working on my PhD as well. So I needed to have a numerical model that accurately depicted what was going on in the real world. And my work was on the environmental influence of bridge structures. And so when you talk about environmental influence, there's all kinds of conditions of loading and weathering and so forth. And so back in those days, the engineer didn't pay attention to temperature effects on bridges. And I kept wondering why would a bridge not do so well in the atmosphere? If you put it indoors, I think it would probably last longer. So there had to be some influences that were really important. It turns out that it was about 30% of the design loads. And so that's changed the codes. And so through that process, not only did we look at it theoretically, I also helped on some research dealing with test values and correlation between tests and our theory. So that's where I got involved in it. And then from there, I actually wrote some programs. I sold a few, but then I decided to do something else. So.
Okay. So we're going to be talking about some of the work that you've done on the World Trade Center 7, but in terms of finite element methods or finite element analysis, how would you describe something like that to the layperson? How would you say, well, this is what I'm doing?
Well, I guess what we could probably do is take a piece of paper and say, there's this beautiful picture on this paper, and I'd like to simulate that beautiful picture. And so if I was to create it in a crossword puzzle kind of thing, where each piece, if it's put together right, will actually look very close to what that picture looked like. That's what we do when we take a big, complicated thing and break it up into little pieces and put it back together. And that's the finite element. That's a finite size that we put together. And it's important to know the configurations and also the geometry shape, because if it's really, really long with respect to its width, it may not be so accurate. So you have to be very careful and understand the implications of shape and size and all that kind of stuff. But it's a very, very powerful technique in that mathematically we can simulate real world conditions. It's not exact. It's an approximate method, but the more elements you have and the more fine refinement you have, the better possibility you have of getting an extremely close answer to what really might happen.
Interesting analogy. So it's almost like a photograph that's high resolution won't look as pixelated as one that with low resolution.
Correct.
Okay. Yeah, I get that.
Yeah.
So, I mean, since you've been working in this area, how have the algorithms and how has technology impacted finite element analysis over the years?
Well, it all started through was called the stiffness method, and then the mathematicians and the scientists and so forth got into this game, and they said, "Hey, wait a minute, we can take and do a better job." Now, stiffness method was an exact method for beams and for different shapes, but when you take and start cutting these things up, and you want to really closely approximate what's going on, then there were mathematicians came in and improved these algorithms significantly. And so that enabled us to really do a really good job of approximating what might be happening on a real complicated structure. And by the way, the World Trade Center, which is what we're going to be talking about here today, is not a simple structure, particularly when you try to explain what may have happened on a given day.
Yeah. Now
September 11th.
Yeah, for sure. And you've worked on obviously cases and things like this over your career. When a structure fails or when there's something in doubt about a particular structure, and especially when there's a loss of life. I mean, I remember here in Canada, there was a mall that one of the parking platforms had just collapsed. And I mean, we can see them on YouTube all the time. But when something like that happens, how would you expect an investigation to proceed?
Well, I would expect that under ideal forensic conditions, you would have a situation and you would have something about that structure you could look at. And if you couldn't look at it, if it was completely collapsed, then you would go to the debris and perhaps like an airplane, you'd start putting things back together. Or if you were not able to do much of that, you would certainly pull out the materials and you would petrographically evaluate the concrete. You would microscopically evaluate the steel. You would look at whether there was damage caused by the conditions that people might think might have happened, which might be overstressed, might be thermal expansion characteristics. All of those things you can pull out and evaluate. Guess what? That was not available here. None of that was available. Okay. Unfortunately, it had been all transferred off out of New York and went overseas for the most part. So that was really, really unfortunate. And so therefore, what do you do next? You're stuck into a pickle that, okay, we got to evaluate this thing the best we can. So we go back to the original set of plans that it was actually built by, erected by, take those, put the structure back together. And so we did it using AutoCAD and finite element to where we could actually look at the building and see if it matched up with the erection drawings and what we would see in the field the best we could.
Okay.
Ideally, I would have preferred to been able to speak to the design engineer, structural design engineer. I would have preferred to be able to talk to the architect. I would have preferred to talk to the owner. I'd preferred to been able to talk to those involved in the construction of it, the material suppliers,
Hmm.
and all of those people would have given me a huge amount of information of which I did not have available to me.
Okay. Yeah. Well, fair enough. I mean, I've been through your report, and let me put that up here. In fact, for those of you who are interested, Dr. Hulsey has a very, very comprehensive report at the link below here. If you can even just do a search for UAF WTC7, and it'll come up in Google probably right away. So, and there's a whole bunch of materials on that particular page. Um, so I want to get into the World Trade 7 Center. So allow me to, I'm going to share my screen here, and I want to go through just a little script that I planned. I normally try to keep this conversational, but because of the content and the type of thing that we're dealing with, it's very difficult to sort of talk about all the components without giving some kinds of visuals here. So let me go through here very, very quickly. And if I'm incorrect in anything, please correct me. So World Trade Center 7 was a 47-story building completed in 1987. It was a steel frame and reinforced concrete floor construction. It was built above Consolidated Edison of New York Electric Power Substation, with its first 3 floors connected to the substation. So down here, you'll see inside of this ellipse here, that's where we've got the original substation. Now, it's about the World Trade Center 7 is located about 105 meters north of World Trade Center 1. So this is, if you see my mouse, that's World Trade Center 7 there. And then down here we have World Trade Center 1 and then World Trade Center 2. So World Trade Center 1 is actually the closer of the 2 tall buildings. Now, World Trade Center 7 is not a symmetrical structure. So you can see it looks sort of like a trapezoid. And if we look at a plan sort of view here, you'll see that we have one end, which is the north end, which is wider than the south end. And so the top end, the north end, is about 100 meters, and the south end is about 75. And you can see shaded is the outline of the Con Edison substation. Now, in terms of the timeline of events for that day, 8:46, American Airlines Flight 11 crashes into the North Tower of the World Trade Center. And unfortunately, it crashes into the 93rd and 99th floors, and it kills all 92 people aboard. And then at about just after 9 a.m., United Airlines Flight 175 crashes into the South Tower of the World Trade Center between the 77th and 85th floors, killing about 65 people aboard. At about 9:59, so just before 10 a.m., the South Tower collapses. At 10:28, the North Tower collapses. Now, the North Tower is the one that contributes to the damage of World Trade Center 7. So World Trade Center 7 is substantially damaged by debris when the North Tower sort of collapsed. And so the story is that the debris ignited fires and that sort of thing. And so what you're looking at here is a debris field, sort of an outline, the largest circles being sort of the extent to which much of the material was found. And right after this, what we had, you can see some of the damage that was mapped out. So the red areas are really what we're looking at. So the view on my right is the south face, the face that's closest to the North Tower. And then the small red section here is a view on the west side. So so this corner that I had there is the southwest portion. Now, the damage, I'll just play this very quickly, and you'll get to see for yourself what is happening here. You'll see that there's a little portion up on the top, the penthouse that's referred to, drops, and then a few seconds later, you'll see that the building just collapses. So there's a few other little videos there. The building from the 7th floor to the 47th floor was supported by 24 interior columns and 58 perimeter columns. And this was a building that had sprayed fire-resistant material. So it's not, it wasn't just a completely just empty steel structure, but there was some, obviously some protection. Now, as the story goes, there was the sprinkler system wasn't working. What I have on my screen here are just 2 views of a model. So this is the south face, this is the north face, and you can see the penthouse up on the top there. So that's kind of where we're getting to. And this building, you can see in the video before that there was some fire or some smoke, but not what I would call a substantial amount. I mean, you could see the back end of the building was pretty much intact. But later in the day, I believe it was 5 p.m.-ish or so, the tower goes down. So that's kind of where we're at, and I'm sorry, I'm going really quickly here, but we have to focus in on some of the details of the report. And there were a number of different reports, and the basic story goes that the fires caused some expansion of these beams. And this particular beam here, this 79, if you're watching this is of particular importance. This is sort of the critical beam that everybody has been really focusing on. And the top end of my screen is the north end. So it's this northeast corner that's important. So there's a number of beams that go across and attach to a girder, which attaches to column 79. And we have some design drawings and that sort of things. This is a schematic that I took out of Dr. Hulsey's report, and you can see here that there's some structure. So this column right here is 79, and then we have some beams and that sort of thing. Okay, so I'm gonna stop there, and I have a question for you, Dr. Hulsey. First things first, the design of this particular building. What is when using a steel frame or a steel structure, what is the benefit, or why do you use a steel frame versus just building with concrete or whatever? What's the benefit?
Well, I think it's more about economics. Over the years, the concrete has been a preferential material over steel, and then a few years later, the steel industry gets more competitive, and then they become the preferential material to build buildings by. So, and you can even see a building start up as architecturally as one kind of building and get changed before it gets to the construction stage, simply for those reasons. So there's a number of and then there's preferences by people on what they would like to have and how they could make it work. Such as a concrete building can be architecturally very friendly, whereas a steel building has limitations. You've got an awful lot of, shall we say, a frame. You got a lot of shop work to do to get a shape that's other than straight, and so there's disadvantages if you want to go to highly irregular curvature kind of conditions to go steel. But something like this, where it's all straight sections for the most part, is probably a good choice to go steel.
I mean, is there anything here that raises any flags in your mind that says, hey, there's something designed poorly or something? I mean, it's built. I mean, they say it's built to code. I mean, the fact that it's in a regular shape, it's not rectangular, does that cause any concern?
Well, it causes complexity and load distribution. It tends to be. I felt like the design of this building was not the most desirable. I thought there was a lot of complexities in it that I didn't think it needed to be there. Since, but in terms of code, I did not see anything in this building that flagged a code violation or flagged a situation that would make it be questionable in that regard.
Okay.
So and I don't know, do I have a minute just to share something with you? I would like to say that when I started this, I announced right away that fire did not bring this building down. And the first thing I looked at, I didn't look at what NIST did. I looked at how that building needed to behave. And it became very obvious very quickly that it was not what was being said. And so I put that out there, and then that was before the end of the first year. And then the other 3 years I was working on trying to figure out, trying to simulate NIST assumptions and seeing what they came up with, and then trying to evaluate the actual collapse, which was not an easy task. So anyway, that's kind of what I wanted to just share with you quickly. The connections on this schematic is not actually what was used to build this structure with. I mean, geometrically, it's a good view. Anyway, are you still there?
Yeah, I'm
Hello?
here. I'm just
Okay.
yeah, I'm just listening. What I'd like to do is just show people. We got to get people's head around this thing. What we're
Yeah.
talking about is the corner here. This is the northeast corner, and then if we get inside, what we'll do is I'm just trying to get in here. You'll see that there's a number of beams here, and so it's this column right here. So this would be column 79 that'd be failing, and the connection here is not correct. This is just a model for visualization, or something that's demonstrative, so it's not fully accurate. But that particular connection looks more like this. So Dr. Hulsey, can you tell me about the seated top clip connection?
Yeah, if you take a look at the picture on your left, you'll see two things that are significant. The column, it looks like an H looking down on the top. And what they did is they came in and they put plates on and welded it to the outstanding legs on each side. So, and those legs actually stood out from the edge of that H. And then they connected the A2001 girder, which is what if you'd bring your arrow down, that's it. And you'll notice that there are stiffeners, web stiffeners right next to the edge. That's it right there. That web stiffener is significant because it stiffens that web and it stiffens the flange down at the bottom. You notice that stiffener is not all the way up. It's only at the bottom where that A2001 is actually sitting on a base plate.
Yes.
And if thermally, what NIST said is that when this thing heated up, that the A2001 slid along the base plate and slid off of that support.
Mm-hmm.
Well, first of all, they forgot to include the stiffener. That wasn't part of their analysis. Secondly, that outstanding leg sitting out there, it could not go past that anyway. In other words, to your left, right there, it sticks out past that flange, and so therefore it couldn't move any further.
Right.
So if everything I did was wrong, it still couldn't have moved past that, and it wouldn't have fallen.
And these stiffeners, they're welded in place, correct?
Yes.
They're welded in place. And the top, this little bracket up top with these, are these studs or bolts? I'm not sure what that is, but this looks like a welded plate, and then this is just...
And then the bolted, yeah.
And then bolted in place. Okay.
Yeah.
So this is important because okay, just for everybody to be clear here, what we're saying is that this beam, there's some other members, beams onto this perpendicular to here, that when they heat up, it's going to push this beam, looking at the view on the right, off here. But like Dr. Hulsey says, there's some portions which are overhanging, which is going to stop here. Plus, you have these stiffeners. These stiffeners were not included in this report, and I think that's super important.
Yeah.
What about the type of modeling that was used by NIST? So, for example, I saw that you had a very extensive model. Let me see if I got it here. So this here, what I have on my screen is the model that was produced by you and your team. What can you tell me about this model in terms of its accuracy?
I would say it's extremely accurate because what we did is we initially modeled it and we used what's called a coarse mesh, and then we kept refining the mesh. And when you don't see any changes to your results, or minimal changes to your results, you're converging in on a solution that you're looking for, and that's what I did. Okay. And so if you'll notice, that green That's just not a solid. That's a whole bunch of little pieces put together to create that shape. And so when we did all of that, we were getting really, really very, very good results in what we were looking for.
Okay. In terms of, I mean, you had mentioned fires and the fact that NIST is saying that there were fires on the building, and you can sort of read in the reports the progression of fires. They actually, and it appears that the south side is the part that actually gets struck, but the fires progress both clockwise and counterclockwise around the building over time. And it's interesting that it's the northeast corner that actually is the part that is that they're saying had failed first. So
Right.
in terms of fires, some of the there was a reference to an ASTM standard, and that fires on the floors. So if something's burning in a room, that the above you, they can reach close to 590 degrees Celsius, about 1100 F, and because they had the sprayed fire resistant material, though, the temperatures typically don't exceed about 400, 750. What can you tell me about steel's response, or the type of material that was used here in terms of temperature?
Well, in this case, I think NIST came out and said that the temperature did not exceed 200 degrees C, and I came up with a similar result. And so that's about 392 degrees F. And so Fahrenheit. And so at that point, you're not getting much loss of strength or change in modulus of that steel. When it starts going larger temperatures, then you start getting a degradation of its capability to carry load and its capability to deform properly. So I don't know if that answers your question or not, but essentially we have a curve in our report that shows how it degradates with temperature, and so in this case, there were fires spread around, but the question is another question that I asked from the day one is where was the uh, where was the fire combustibles at? What produced it? Because most of these were um, financial operations or governmental operations, and they would have had everything in safes. I don't understand where all the fire combustibles were coming from, other than coming in from the building that fell down, World Trade Center, the other World Trade Center buildings.
Right.
So
It's an interest. So these are just office fires, or whatever you have,
yeah,
and people might have a printer, your desk, your chairs, your whatever other materials you're working on, and that
sure,
would be this. That's the source of the or what's burning.
right.
So I guess the question is, though, in your models, did you use the the retardant material in the model, or did NIST use it, or is it not used?
I did not use it,
Okay.
and that's conservative because I wanted to see if we had the fire going in there, what conditions did we have to worry about. I did it. There was what do we call it? On the floor, it's a concrete floor connected to these steel beams and girders, and of course NIST didn't account for the fact that there were shear connectors on it, but there actually were. So that made it stronger than they would have thought otherwise. But underneath that, it was a drop it down ceiling, and that was a cavity. And I did look at the temperature migration through that whole scenario as well, which I wasn't sure if it would make a difference or not. It didn't make much of a difference, but I did look at that. And so the thing that is kind of interesting is that the concrete system, the concrete steel system, acting compositely, does significantly enhance the strength of that system under any duress that's going on. So
Okay. So let's talk about the reports for a second, because I want to understand what NIST and maybe others have suggested about this particular area. And so when it comes to this particular area, they're suggesting there's fires, and then this beam or this girder falls off of column 79. So how does that relate to these other beams that are moving across here?
Well, keep in mind that NIST looked at the exterior of the building to be fixed. In other words, couldn't move. And so if you put your, I guess your pointer up to number 40 on the exterior, that kind of gives you an idea of the east side, northeast side of this thing.
Mm-hmm.
And if it starts expanding, it's going to start moving with respect to that line 3540. And in all the movement then moves towards 79 and 44.
So the assumption that they're making, this boundary condition they're saying, is that the outside wall is not going to move, even though there's nothing on the other side to hold it back.
Correct.
They're suggesting that it's fixed rigidly and that everything is going to move to the west in our case.
Correct. That being said, there are beams through there, like at 79, but to the right of it. In other words, going from 79 over to the line 3540, there's a beam going from at 79, column 79, from left to right. You go upward, you get another one left to right, go
Mm-hmm.
up, another one left to right, and then at the very top near 4442, you got one going from left to right, but there's members that are crossing, coming down and fastening to it to give it buckling resistance as and it's framed into the exterior wall system. Okay, so all of those heated up. And that one up there buckled per NIST, but if they put those little beams in there, which they didn't, it wasn't going to buckle. And so all of that stuff affected what was going to happen on girder A2001, which was framing from 79 to 44.
Okay. Now, did NIST use, in their assumption, did they assume that there was no fire retardant material as well?
I'm pretty sure that that's the case. I'd have to go back and review that again.
Okay.
But we did look at it as the same way that they did. Okay. I wanted to give it the benefit of the doubt so that there would not be, any questions about whether we may have. The only thing you can do in a case like this is you look at the maximum and the minimum, and see where you are within it. And you want to make sure that you haven't described something that's not even remotely possible.
Well, I guess that's my question was going to be: is there some kind of what would be the reason for fixing the outer wall? A beam?
I have no idea. It's not fixed.
No, it's not.
It's flexible.
Yeah, well, that makes sense to me.
So the very first thing less than a year in, I said, wait a minute, this thing is actually not moving to the west. It's moving to the east. So,
interesting.
So if you really stop and look at the thermal expansion of this floor system, the stiffest area within that floor system thermally is near the elevator shafts. And so the movement, if you heat up this floor, it's going to be somewhere near those elevator shafts, and it's going to move in all directions with respect to that point. So the relative movement actually at column 79 was not anywhere close to what they said it was between the column and the girder.
Interesting.
So
okay.
Anyway.
So just to be clear for the people listening, what NIST is suggesting is that this outer wall is fixed. These beams here start to expand, and they've left them free to expand. So they're basically free to expand. There's none of these small little smaller beams here that are connecting this one, and basically that this girder here crosses past the column, and even though the column design that we just discussed has some overlapping points which would block the girder from passing, They still had made it. Now there was a change to their report, and can you tell me about the difference? So there's like a 5.5 inches versus a 6.25. Can you explain what happened there?
Well, that bearing plate is 11 inches wide, and they were coming back, and they had 5.5 inches was their relative movement between A2001 and that girder and that column 79, which would, and then they discovered, oh my gosh, I don't know what their purpose was, but they then came back and said it's got to be 6.25 inches of movement,
I see.
which would have shoved it off
Okay.
if there weren't any restrictions.
Right. Well, that's yeah. If it was free to move and you just basically disassembled everything or
Right,
got rid of
right.
some certain things.
Yeah.
In another report, so this was the there was a difference, and I don't remember if it's the Nordstrom report. So there were four reports. There was FEMA, which is the Federal Emergency
Right.
Management Agency, that was issued in May of 2002. There was NIST, which was in November 2008. But there was also some little litigation going over this particular building. So there was something. What was the company called? Arup and Partners, and Guy Nordensson. So I guess it's the Nordensson report, which was issued in April 2010. And then there was another one, which was the Defense Weidlinger Associates, and they came up with their own sort of theory as to what happened. But it's interesting that in the Nordensson report, actually, they're suggesting that the opposite happens. So if we go back to our little model here, what we were talking about in this figure, what they're suggesting is that I believe these beams are buckling.
Sagging, I think.
Or sagging, excuse me, sagging, right.
You're right. And due to a load coming down on them, and we examined that. The other thing, they didn't give any credit to the concrete fact that the concrete and the steel was working together, giving a huge amount of stiffness there. But the point load that they put on it was not an accurate point load. It was a dynamic load that was spread over an area, and so the amount of load actually being imposed, we don't agree with what they had in that respect. So,
okay.
And I'm bothered by the fact that not a lot of credit was given to the concrete floor system by any of these people. In reality, that floor system was pretty significant, and I looked at it thermally as well as just structurally. So,
and when you say that, and what you have, if I understand it correctly, you've got some metal plates sheeting it's sort of a corrugated, I guess you'd call it, and then there's concrete poured into that, and they're fastened. There's like studs that hold the two together, like rebar almost. Okay.
Yeah, well, there's reinforcing bars in the concrete, but there's also what's called shear studs, which is like bolts that are welded into the flanges of those girders and beams. And that then concrete is poured in what is stay in place forms called, and they've got flutes. Those flutes are such that they actually give them added strength in one direction, different strength in another direction. That makes it further more complicated.
Yeah.
Because it's not going to deform the same way thermally because of the matted concrete. And by the way, the thermal conductivity of the concrete is quite different than it was of the steel.
Mm-hmm.
And so you've got that issue going on. The thermal expansion, or the thermal, shall we say, the thermal properties are quite different between the two. And it's a function of the aggregate that goes in there. So,
okay.
Anyway, we looked at all that.
Okay, so let's say, for just hypothetically, let's say that for whatever reason, the connection at 79, column 79, it's free to move, and we get this girder that falls. It falls off of its support. So at that point, so in my mind, when I think of the steel structure, I see this lattice, all these interconnected beams. And so, if you remove one connection, I can't imagine everything just disappearing, like everything just progressively collapsing. So is it possible for that girder to fall off and then successively cause, start this ripple effect where one, it's progressive effect where the next column fails, the next column fails, the next beam fails, and so forth.
Well, you can certainly simulate that, but the problem is this building is not symmetrical. So if you start playing that little game, and it's going to tilt. It's not going to be, and we did examine all that. It's not going to come down as the video shows you. So that whole scenario is not something that could have happened. It just, I mean, there's so many reasons why it couldn't have happened. So, that's just another. So we looked at interior columns coming out. We looked at exterior columns coming out, and in various stages, almost every, a tilt. So what we did is we ultimately finally took and we started saying, like, what could have happened to create what we see? And it became very clear that we had to take out all the interior columns and the exterior columns of slightly after that point in time, and that would have enabled it to come straight down.
That's interesting. Now, the Weidlinger Associates report actually says that this beam will come down, but there was also other floors that were coming down. But the temperatures that they were using were twice what they're saying, something up in the range of 800 degrees Celsius on these other floors. But I guess the question is, what's the source of fuel at that point to cause that?
And where were most of the fires anyway? They were on the 12th. It's certainly below floor 13.
Mm-hmm.
So
yeah, no, correct. So also to clarify, when you talk about this progressive, or the modeling that you did in order to sort of simulate what we see in the video, you're literally cutting the connections at all the beams, or is that what you're doing, or how you're modeling that?
Well, over 8 stories, we cut the columns directly off so that they couldn't provide lateral support, or they couldn't provide axial support. And that enabled them to move down as a unit, enough to be able to move the whole thing down. I think if I recall correctly, I think it was at least 8 stories that we had to have to make that happen.
Mm-hmm.
And then the exterior slightly after that. But in reality, that column 79 up there actually had to come down at the top between floor 45 and 47 to supporting that the penthouse up there,
the penthouse.
At the top. Yeah.
There's on your website, actually, there's a reference to a YouTube video. So it's this one here. I'm just going to shut the sound off. But if what Dr. Hulsey is referring to is, you can see this penthouse, it just goes down. And so something internally has to cause it to fail. But yet we don't see anything on the exterior that goes down until everything just sort of falls. And that's sort of an interesting point too. And let me just play that again, is that how can everything on the inside collapse and still have the exterior intact until it just drops straight down?
Well, that was about a year's study right there.
Yeah.
So many questions about, can you even get anything to happen like that?
Right.
So.
Well, I mean, the implications of what you're talking about, obviously, and again, World Trade Center is obviously, everything is just controversial. So I wanted to keep this on the science, and I want to keep this on your report. But if you take the time to read it, and I would suggest for people to really sit down and start going through it, and it's not an easy read, I'll give you that. You have to sit down and really look at it. But once it does click, you'll start to see where all the problems rest and lie with the NIST report and some of the other reports. And so, so I understand what you've done. And I understand also, we talked about this the other day, which is You're not trying to suggest what happened. You don't have an explanation exactly for everything that happened on that thing, but you can say what didn't happen, right?
That's correct.
Yeah. Okay. And I think that's a fair statement.
Yeah.
In NIST's own, because NIST did in their own modeling, they had their own sort of simulation that they did. And did they stop it at a certain point? Because I don't actually see it ever like coming down all the way.
It probably did. I'm not sure about that. The model just seems like it does not really describe what went on there.
No.
And they had a great piece of software. And so, that was, I don't know what the issue was.
Actually,
So,
well, let me ask you about that. Yeah, let's talk about the software. So you actually you did this twice, in fact. So you had and how you may want to just give a plug to your students, the research. Actually, you had a postdoc too, I believe.
No, I didn't.
Oh, okay.
But I had two PhD students.
Okay.
Each one of them using a different computer program. One was using Abacus, the other using SAP, and we would do the simulation, and then we would have both of them doing it and seeing if they got good correlation. We did that, and then I would review it, and so we would have a discussion. We would have a critique. It was a quality control methodology that I was using to try to make sure that when we looked at anything, that we had scientifically evaluated it correctly. And so before we would move on to another step in the process.
I see. And in the end, when you were, for example, when looking at the thermal expansion and the movement of the girder at column 79, what kind of numbers did you have, or what kind of differences did you show up?
Between the two,
Yes.
hardly any difference. I mean, within a shall we say, eighths of an inch or something like that. It was just very little differences.
Okay.
And between the two models, and the two programs. I mean, both programs are very, very good at what they do. SAP 2000 was generated by Edward Wilson initially at University of California, Berkeley. And the Abacus was put together by a private group. And it's just, both programs are excellent what they do. The learning curve on Abacus is much higher, however. So I felt like scientifically Abacus would do a really, really great job. And I'd used it before, and it really kind of gives you the ability that if it isn't able to do everything, you can write an algorithm to add it to him and give it the capability to do it.
Okay.
And so, I mean, it's really quite powerful. SAP, on the other hand, is really, really quite powerful, but it also enables you to get things done quicker. So there's a there's a benefit to that process.
So which one did you mentioned that NIST had a good program? So which one did they have?
Shoot, I think it was LAN or something like that. I can't remember the name of it right this minute, but it was a good. It's an excellent program. Excuse me for a second.
Well, I guess the problem I'm having here is trying to figure out why an agency like NIST, who have very good people.
Absolutely.
I've met people there. They're very good. There are some very strong minds there, some very good people. How they could let something like this pass from a quality control standpoint. I mean, there should have been a lot of peer review done, just following up a simple process like you would when you publish a regular paper. Right. And somebody would have had to have seen this and had to approve this thing for publication. So I'm trying to imagine in my mind why something like this would pass, because it was interesting. I watched a video the other day of somebody asking you straight out, and I'll ask you here, but if a student had handed in a paper doing this exercise to you, would you give them a pass or a failing grade?
Well, that question was actually asked of me, and it would have to be a PhD student to ask that question, and I would have flunked him.
Yeah. Yeah.
it's you got to be correct when you do something. I don't know why they had it. They missed all these steps, but they're an excellent group. They do outstanding work.
Hmm.
I just don't know what the answer to that is.
Okay. So let me ask you, what's next for you at this point? I mean, you've done the study. You sort of, it is what it is. It makes a very strong point for sure. But what are your plans at this point?
Well, I'm going to write a couple papers, peer-reviewed journal articles on it. Um, and then, I just retired, so I'm in the process of re-examining what I'm going to do.
Okay.
Uh, so, yeah, I think that's definitely where I'm heading right now. So,
Okay. Interesting. And how how has your study been received by architects, engineers, and sort of the scientific community in general?
I don't know the answer to that completely. I do know that there's uh, a I've given a presentation to several people, several engineering groups, and they've all been incredibly they've really received it well. It's you might go, sometimes people go into these things thinking one thing, and you see them transformed automatically when you start providing the compelling evidence of what we found. Then I haven't seen any that left saying, "Wow,
Yeah.
that this is truly something to think about."
Yeah.
So
There's well, obviously there's a mountain of information on YouTube, and I didn't want to get into the controversy and such, but even for myself, I didn't want to. I mean, I know that, there's bias and that sort of thing. So what I did was I was watching debunking videos.
good.
So I was watching videos that actually posed the other side, and there were some good points until I read your report.
Yeah,
There was some good points, right? Why something happens or why something didn't happen. I mean, and there are other things that we aren't discussing. So, for example, some of the I believe it's in your report as well, but some of the metal which was found, and I forgot the exact term of what it was called. I have it here, but it had something to do with eutectic. It had something to do with an elevated temperature.
right.
Yeah, so which gives evidence, or is a type of evidence, but basically says that just a standard office fire is not going to provide sufficient heat or temperature
That's correct.
to the metal, right? So there has to be something else there. And as
Yeah.
another point too, that because of the substation that was there, I think everybody agrees that there's no diesel fuel or some other fuel that was pretty much left intact, if I'm not mistaken. I
Mhm.
shouldn't say intact. Of course, the building collapsed, but what I mean
Yeah,
is that it wasn't a source
right.
of fire.
Yeah.
Okay.
So in the past and today even, I don't want to get into the controversies because uh, my report, the way I see it, is it was based on pure science. I tried to not allow anything that might have been a possibility of somebody thinking one thing and or feeling a different idea. I would listen and read the science aspects, but not what people might be saying on the street.
Hmm.
So um, let the package stand for itself scientifically.
Well, I think that's I feel the exact same way. So I was not going to ask you anything like that either. And I think, what, this is probably a good point to end the conversation on a note like that. We'll just leave it with the science and let it
Yeah.
speak for itself. Well,
Okay.
look, hey, listen, I can't tell you how grateful I am. Some great information. I want to commend yourself and your team. The report is really well done. It's very well
Thank you.
organized. It's well written. It reads well, and I don't always enjoy reading papers. I have to tell you that it's not always a fun thing to do, but I actually was interested in reading this, and it sort of caught my interest. So,
Good.
um, do me a favor, just hang back for a second. I'm just going to make some
You
closing
bet.
comments, and then I'll come back. Great,
You
thank you
bet.
very much.
Yeah.
All right, everyone. Well, that does it for episode 12. Next week, I'm going to be interviewing David Cam. And if you don't know about the David Cam story, he was wrongfully imprisoned for 13 years for triple murder, something that he didn't do. And it was the murder of his wife and 2 children. There was a big controversy about the David Cam case in the bloodstain world, and quite a lot of information. And the nice part is we're going to hear it right from David Cam himself, and how things were perceived from his end. So on that note, everybody, hey, thanks a lot. Great talk today, and hopefully I'll see you again next week. Bye-bye.